Hi, so welcome to this lecture. We will work out the solution of the classwork problem that was given a couple of days back. So this was the differential equation. It's a second order linear differential equation but with non-constant coefficients. Okay, as you can see, the coefficients of dx, dt and x are tan t and cosine minus cosine squared t respectively. And so these are non-constant coefficients. They are functions of time. And of course on the right hand side we have some input and we're going to solve this. And we're going to use the same technique that we used while solving the Cauchy-Euler form of second order linear differential equations with non-constant coefficients. And so let's just see how we can do that. So remember, while we were solving the Cauchy-Euler form of second order linear differential equation with non-constant coefficients, we really took the trial solution. So first we are going to solve this differential equation with 0 on the right hand side. In other words, we are going to find the homogeneous solutions. Okay, homogeneous solutions of this differential equation. Solutions of the homogeneous form, it means 0 on the right hand side. So first let's do that. Let's say we have 0 on the right hand side. Okay, and we are going to find the solutions to this, which will be the homogeneous solutions. Remember, while we were solving the Cauchy-Euler or doing the Cauchy-Euler method, the trial solution, let me write xt for trial solution. The trial solution we took was really t to the m, but it was not t to the m can be written as e to the m log t. Okay, this is a natural logarithm of time. Okay, now, so far, before when we were solving differential equations with constant coefficients, we had only t over here, only time over here. Okay, but for non-constant coefficients, the one that had the form of the Cauchy-Euler differential equations, the function that worked with m over here was log t. Okay, and we're going to use the same technique. We're going to find a function which for now let's call ft. We're going to find a function which sort of works for this differential equation. We'll have to figure out a function ft. So for this differential equation, we don't want this to be log t. We hope it's going to be something else, so we have to find that. So this is going to be e to the power m times some ft, which should work for this. In other words, somehow reduce the non-constant coefficients to constant coefficients. Okay, so that's what the objective is. We have to find ft in a manner such that this problem becomes a known problem. In other words, a problem with constant coefficients. And the little trick that works, and I think many of you got it while doing the problem, was just to multiply throughout by sec squared t, just to eliminate this non-constant term here. So if I multiply throughout by sec squared t, this one goes. Okay, all you have is just a minus x over here and 0 on the right hand side. You have a sec squared t term over here, and here you have to squeeze in that term as well. So you're going to get a tan t and a sec square t. Okay. So what happens is that, so you get this non-constant term here, and if this is going to be the trial solution for this, it means that you have to, instead of x, you have to put xt. So in other words, you have to differentiate xt twice. If you differentiate xt once, the one that comes down here is mf prime t. Okay? Because if you differentiate this exponential term with this function here, the term that you're going to get here is this whole thing differentiated. So you're going to, so xt differentiated is going to get you mf prime t e to the mt, e to the mft. Okay. Well, if you're going to do it once more, then again this term should come down. Well, there will be other terms because you have to differentiate this now, but this will again come down to make it m squared f prime t squared. So really another differentiation gives you this term, f prime t squared e to the m ft plus something else. Okay, but that's what the clue is. We need a term f prime. So once you put this in there, okay, this term is going to come down here. okay, f prime t squared, it's a function of time, which should somehow eliminate this x squared t. We want this function ft to be such that it takes care of this x squared t term and makes it and nullifies it, so that now we have a constant coefficient here. And function, a known function that should nullify sec t is cosine t. Okay, so if my f prime t is cosine t, then f prime square t is going to be cosine square t, and cosine square t should always nullify sec square t and make things constant. So so if f prime t is a cosine t, then ft should be a sine t. Okay, that's the clue, and that's how we should start. So let's start with this clue. Let's say that ft is sine t, and I think many of you guessed that already. So we'll just work this out. All of this is just scratch work. We'll see how this works, okay? So, xt prime, as we've just seen, is going to bring this thing down, but with a differentiation. So, m cosine t e to the m sine t, okay? And then a double differentiation, xt double prime, a function of t, should again be, so let's differentiate this one first. So, it's going to bring this down again, but with a differentiation. So, you're going to get m square cosine square t e to the m sine t plus differentiation of this one, which should give you a minus sign. So minus m sine t e to the m sine t. Okay. All right. So let's just put that in there instead of xt. Instead of this double differentiated x, I put this one. Okay. So what I get is, so I'm going to get the sec square, which will multiply this, okay, this one. The sec square t and the cosine square t will just give you 1. So you're going to have m square, this thing, e to the m sine t. The sec square will also multiply this one to give you a minus m sine t. Let's just write sec as cosine by cosine square t e to the m sine t. The tan t and the sec square t, so let's write this as cosine square t. You have the dx dt, which is really this, if you're substituting xt for x, okay? So this term multiplies this term, okay? What do you get? What you get is that you're going to get tan t and a sec square t, which came down as cosine square t, and m cosine t. So this should give you plus m. Okay, we can write the tan t as a sine t divided by a cosine t, and so you have cosine cube t in the bottom, and you have a cosine t on top. So you're going to get a cosine square t. I hope that's clear. Okay, you have a cosine t. You're substituting for dx dt this one. So you have a cosine t there. You have the m there, but the tan t will become sine t and cosine t, and one of the cosines will cancel with that cosine, so you will be left with cosine square t. And of course this one, e to the m sine t. Okay, I think that's clear. And these two will cancel, okay, as is clear. Minus, you have this x. This x here is, of course, this one, okay? It's going to be e to the m sine t equals 0, okay, on the right hand side as usual. So these two will cancel, and these two will have e to the m sine t common, which I can take out, but that's a non-zero factor, which I can eliminate because you have 0 on the right hand side. So really what you get is m squared minus 1 equals 0. So the two roots, this is the auxiliary equation, remember? And so this is going to be plus 1 and minus 1, the two roots. Okay. Now, of course, this is, so the ft, so ft equals sine t works. Okay. So what are the two complementary, so what are the two homogeneous solutions of this? Okay. So the two homogeneous solutions are going to be, so if you substitute for m, the plus 1 and the minus 1, those will be the two homogeneous solutions. And the complementary function, so the two homogeneous solutions are e to the plus m sine t and e to the minus m minus 1, which is minus sine t. Okay. And the complementary function is just going to be a linear combination of these two. And that's just one part of it. So you have found the complementary function of this, okay, by that substitution, okay. All right. Now we have to solve this for the particular solution, okay. But before we go on to solve the particular solution, it's better to write sine t as some other variable, and I think the reason we want to do that is because this is the complementary function in terms of t. Okay, if I write sine t as z, then if you view the complementary function as a function of z, then this becomes c1 e to the z plus c2 e to the minus z. Okay, in other words, these two are the complementary functions, these two are the homogeneous solutions of a differential equation whose auxiliary equation has roots plus 1 and minus 1 like this. So the differential equation whose complementary function would be this, the differential equation whose complementary function should be this, is going to be d2x dz2 minus x equals 0. Is that fine? Because if you have this differential equation, then the auxiliary equation for this is going to be this, isn't it? This is the auxiliary equation for this. Just substitute m for the double differentiation and 1 for this one, and this is going to be the auxiliary equation. The auxiliary equation will have plus 1 and minus 1 as the roots, and so this differential equation will have this complementary function. So the differential equation which corresponds to this complementary function is really this. And so what this tells us is that by this substitution, if you substitute z for sine t, in other words, we were working with the independent variable t, but if you substitute for t a new variable z, then the differential equation, the left-hand side of the differential equation, in terms of the new variable, where we replace t by z, becomes this. So this whole rather messy-looking left-hand side, or the differential side, you know, this side of all the differential terms, becomes very clean once you substitute z for sine t. And it becomes a very manageable differential equation, and it has constant coefficients. Okay, so therefore, instead of solving this differential equation, I think it's better to solve this differential equation in terms of z, and because I know what is z, I can finally put back the sine t and I will get my answer. Okay, so that's going to be the strategy. So really, the differential equation we started with was sine t on this side, but in terms of this new variable z, the left-hand side becomes this. What does the right-hand side become? The right-hand side becomes, well, sine t is z, so we don't want to keep t anymore. We're doing this in terms of z, so this is just going to be, oh, sorry, there's a slight mistake. This was sine t when we did not multiply by sec square t. Okay, before that. So after we multiply by sec square t, the right-hand side should also get multiplied by sec square t, which is divided by cosine square t. So the right-hand side is really this now. Okay, I hope that's clear. The sine t was there before we multiplied the sec square t term. So this is going to be sine t, which is z, and 1 minus sine square t is cosine square t, so that's 1 minus z square. So really, this is what we're going to solve. Okay, so let's just solve this. Okay. And once we solve this, we will be able to solve this in terms of t. So this is what we are solving. d2x dz2 with this new independent variable minus x equals z over 1 minus z square. Now this is a right-hand side which we have not seen before. We've seen exponential types, we've seen polynomial types, we've seen trigonometric types like sine and cosine, we've seen some products like with product of a polynomial or product of x with another function, product of an exponential with another function, but this is a new type of input which we've not really seen. So you can try this with variation of parameters, but it's not, you're going to get recurring integrals, so it's not going to work out so well over there. So what we're going to do is we're going to try something new to solve this problem, and that's really the purpose of this problem. It introduces a new technique to solving differential equations. What we're going to do is we're going to transform this right-hand side into something which is similar to what we've seen before, a polynomial, okay? And for that, we need this very important formula, really. It actually comes from Taylor's series, but it's the geometric sum. If you have a sum like this, 1 plus a squared plus a cubed plus dot, 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 this sum can be written as 1 over 1 minus a. Of course, if this is true, that is mod a is less than 1. If this is true, then this geometric sum of powers, it's a power series, okay? It's a series of different powers of a, is 1 over 1 minus a. And this is what we're going to use. Suppose we think that z happens to fall in this category, that z squared, the mod is less than 1. Suppose we want to solve the problem for a z like this, okay? And that would be true if you think about it. Z really is sine t, and mod of sine t cannot go beyond 1. Okay, so we are in that region as well. So this is not something new that we're doing. Okay, Z really is sine t. So this kind of happens anyway. So for that we really want. So therefore, if I want to write this 1 over 1 minus z squared term here, if I compare this with a, I can write it out in this series, okay? And so what I get here is, of course, this thing, I get 1, I get 1 plus z squared plus z to the 4 plus z to the 6 and all of that. Of course, all of this is multiplied by z. So what I get is z plus z cubed plus z to the 5 plus dot, 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 okay? That's like a polynomial, but not really a polynomial of a finite degree, but it's a polynomial of an infinite degree, okay? There's no end to this. So that's why I said that we can transform this into something which is similar to a polynomial, and we've solved polynomials, okay? We've solved them by the method of undetermined coefficients, where if there was a polynomial of degree n, we took the trial solution for the particular solution as a polynomial of degree n with general coefficients with a0, a1, a2 like that, and then we had to find those coefficients, and that would be the end of the problem. So we're going to use a very similar technique here. Because the right-hand side can be written in terms of this infinite polynomial, I'm going to assume that the trial solution for the particular solution is going to be an infinite polynomial like this, okay? a0 plus a1 to the a1 z to the 1 a2 z squared plus a3 z cubed plus dot, dot, dot. We don't end it anywhere because this goes on and on, because the right hand side goes on and on. And these are the undetermined coefficients a0, a1, a2, a3, which we have to find, okay? Well, if you think about it, we'll come to that. So we want to try this as a solution for this. So we have to differentiate it twice. So let's differentiate this once. What we get is, this is a constant term, so that vanishes. We get an a1 from there, plus we get 2a2 with a z. We get a 3a3 with a z square, and this goes on and on. We differentiate this once more. We get, this one vanishes now. We get 2a2, okay? The z becomes 1 with the differentiation. Then we get, this 2 comes down, so we get a 3 and a 2 as products, and we get a3 z plus, the next one is going to be 4 times 3 a4 z square, something like that. Okay. Now, sometimes it's easier to just write it in terms of a summation. I think if you write this as n from 0 to infinity, a n z to the n, this, all of you know this, this can be written out as summation n from 0 to infinity. Well, if you look at it, this really is 2 times 1. So when n is 0, I need a 2 there. So I get an n plus 2. I get 1 less than that, n plus 1. A n plus 2, because these two indices are the same, 4 and 4. And I get a z to the n. I guess that's correct. Okay. When n is 0, you should get the first term. When n is 1, you should get the second term. When n is 2, you should get the third. When n is 0, you get a 2 and a 1, which are these two. And you get a2 because n is 0. And you get z to the 0, which is true. You have a z to the 0 here, which is 1. If you take n as 1, you get a 3, 2, which are these two. You get a3 because n is 1. And you get z to the 1. Here you have z to the 1. Okay, so that works out. Right. So this is this, okay? I'm substituting xp for x. So instead of this, I'm just going to write this. And I'm going to subtract x, this one for x, okay? So this minus this, with x substituted xp is going to be this minus this for the left-hand side. So let's just do that directly from this one. If I write them under this summation sign, this minus this, they all have, for every n, they have z to the n common. So what you have is n plus 2 times n plus 1 a n plus 2 minus a n z to the n. That's the left-hand side. Because this is now this, and this is now this. So this minus this is this minus this. And all these terms have z common that I've taken out. Okay. And the right-hand side is really this. Now I want to write the right-hand side as a summation term as well. So let's just do that. It's going to be n from 0 to infinity. I want to write this as z to the n because I want to match every coefficient. Okay. What's it going to be? Well, these are all zeros when you have the even powers, and they're ones when you have the odd powers. Okay. So 1 plus minus 1 to the n plus 1. And then if you divide by this 2, I think that will work out. That's just another way of writing this, okay? It's a very easy and a familiar way of doing this. So if n is, so let's see if this gives us this series. When n is 0, the first term, if you think about it, it has, so z to the 0, this is z to the 1. Z to the 0 has a coefficient 0. If I put n equals 0 here, I get minus 1 to the 1, which is minus 1. So plus 1 and minus 1 will cancel, and you have 0 when you have z to the 0. When n is 1, in other words, for the next term, when n is 1, I have z to the 1. This coefficient should come out to be 1. So when n is 1, this is minus 1 squared, which is 1. So 1 plus 1 is 2, and that divided by 2 is 1. So it gives you this. So it goes on, okay? So this gives you that series, okay? So therefore, we have two series on two sides of this equality sign, and power series, okay? And so all the coefficients of every z to the n should match. So there's going to be a term-by-term matching here. And so therefore, what we have is, we can write down everything. So for all n now, so therefore for all n, what we have is n plus 2, n plus 1, an plus 2 minus an is going to be half 1 minus 1 plus minus 1 to the n plus 1. So you had to remember, you had to find a0, a1, a2 and all of that. And now we have many equations. So for all n, we have an equation from which we are going to actually find this. Okay. All right. So let's just see what we can do with this. Well, what we can do is, when n is an even number, okay, when n is an even number, what happens is, this is 0, because it gives you that series, okay? For every n to be an even number, whenever n is an even number or 0, the coefficient is 0, because this is that series. So, when n is an even number, you have a 0 on the right hand side. So, an plus 2 can be written as, or let me just write it up on top here, okay. So when I want to write n plus 2 in terms of an plus 2 in terms of an, so when n is an even number, this is 0. So I can bring the an to the right hand side and divide by this factor. So this is going to be an by n plus 2, n plus 1 when n is even. And when n is odd, remember all of this was 1. For every odd power of z, all of the coefficients were 1. So for when n is odd, this is going to be, you have a 1 on this side, bring the an to that side, you have a 1 plus an, and then you divide by this factor, it's going to be n plus 2, n plus 1. That's your an plus 2 in terms of an. So what this tells us is that, suppose I have my a0, okay, whatever it is, I want to find a2. The way I can find a2 is, this is n is even or n is 0, okay? This is true. So when n is 2, I can find a2 to be a0 by 2 times 1. Is that clear from the first equation? When n is 0, you have a0, and the difference between the indices is 2. If this is n plus 2, this is n. So if I have a 2 here, you have a a0 there, divided by, well, this n plus 2 is over there, and this is 1 less than this, so this by this. So a2 can be written in terms of a0 like this, okay? And a4 can be written in terms of a2 by a2 as a2 by 4 times 3. Similarly, a6 can be written in terms of a4 as a4 by 6 times 5, and this goes on. So once you know this a0, the first initial term, for example, you know all the even terms in the sequence of a0, a1, a2. So that's one thing that you have to know to all the a0s, or all the a's, is to, or at least the even a's, is to know a0. Once you know that, all the even indices are determined, okay? Well, similarly, if I want to find a3, well, now if I want to find a3, then I can use the second one, because now we are in the odd part of it, okay? This a3 will be related to a1, as you can see. This is n plus 2 and this is an, by 1 plus a1 by, well, the same factor. So if this is 3, you're going to get 3 and a 2. A5 is going to be 1 plus a3 over 5 times 4. A7 is going to be 1 plus a5, 7 times 6. So again, if you know a1, Then you know A3, and once you know A3, you know A5, because A5 you get from A3. Then you know A5, you know A7, because A7 you get from A5. So the two crucial terms here are A0 and A1. Once you know these two, then the entire series, the entire sequence of the undetermined coefficients is determined. Okay, and really there's nothing in the problem which tells us what these are. So these are really in our hands. And let's just use that power to make these two, A0 and A1, the simplest numbers possible. What are the simplest numbers possible? They are zeros. Let's just make A0 and A1 0. As I said, there's nothing in the problem which told us what these two would be. So this really is completely our choice. Okay? And so once we have this A0, well, if A0 is 0, then A2 is 0, because you have 0 divided by something. Then once A2 is 0, A4 is 0. Once A4 is 0, A6 is 0. So with this, you have all the odd, all the even indices, they're all zeros, including A0. Of course, that's the choice. Okay. What about the odd terms? If A0 is 1, let's just work that out. A3 becomes, A0 is 1, it becomes 1 over 3 by 3 times 2. That's not 0. Okay, good enough. What about A5? A5 is going to be 1 plus A3, which is 1 over 3 times 2 divided by 5 times 4. That's just, if you simplify this one just, this is going to come here. So you're going to get a 1 plus 3 times 2 on top and a 5, 4, 3, 2 in the bottom. And if you look at it a little carefully, you're just going, this is a 3 factorial term. This is a 5 factorial term. 5, 4, 3, 2, there's a 1 there. And this really I can write as a 1 factorial. Okay? So A5 gets you 5 factorial in the bottom and 1 factorial plus 3 factorial, which is the previous odd number of 5 up to a sum up to there. Actually, A3 can be written like that. It's 1 factorial by 3 factorial. What about A7? I think A7 should be 7 factorial in the bottom by this, okay? And I'm going to get 1 factorial plus 3 factorial plus 5 factorial. The number which is the previous odd number to 7, like here. I think we should get that. Let's see if we get that. A7, if I just do this for one more term and satisfy myself that this is going to be this. So A5 is going to be 1 plus, A7 is going to be 1 plus A5, which is this. 1 factorial plus 3 factorial by 5 factorial divided by, A7. This is this is A5 divided by 7 times 6. So that's going to be, again, this 5 factorial comes here. So you have a 1 factorial plus 3 factorial plus 5 factorial in the numerator. And this 7, 6 will multiply the 5 factorial, which will give you the 7 factorial. And so really, it's true. So for any odd n, your an is going to be 1 factorial plus 3 factorial plus 5 factorial plus up to n minus 2, the previous odd number, because n is odd, divided by n factorial. That's your, so you have determined all the coefficients. Okay, the even ones are 0 and the odd ones are this. Okay, and so therefore, let's just finally write out what the solution is going to be. The solution, which was, this was the trial solution, and we have found out all the undetermined coefficients, so it's no more a trial solution, it is a particular solution. So what was this? This was A0 plus A1 Z plus A2 Z square plus A3 Z cube plus A4 Z to the 4 A5 Z to the 5, like that. Well, A0 and A1 are 0 by our choice. A2 is 0 because A2, this index is odd. A3 is not 0. A3 we know. A3 is this. A3 is going to be 1 factorial over 3 factorial z cubed. Plus A4 is 0 because this index is even. A5 is going to be 1 factorial plus 3 factorial by 5 factorial z to the 5. The next one is going to be 0, but the next one is going to be non-zero. It's the A7 term, 7 factorial by z to the 7. And this is in terms of z. Remember, we were solving this differential equation. So the particular solution is in terms of z, okay? But really, this is the differential equation coming from the original differential equation, which was in terms of t. So if I view this in terms of t, all we have to do is to just substitute for z sine t, because that's what it was. So it's just going to be 1 factorial over 3 factorial sine cubed t, plus 1 factorial plus 3 factorial by 5 factorial sine to the 5t, and this is what the solution is, okay? Because z was sine t, and this was a substitution which made the rather difficult differential equation with non-constant terms into this rather simple one. Well, not so simple because the right-hand side was different, but it gives us a new technique of solving this differential equation. So that's your particular solution. And so if I just want to write down this general solution, it's just going to be the complementary solution, which was the one with e to the sine t and e to the minus sine t, the linear combination. And whatever we found this particular solution to be, this will be a general solution. Write all of them together, that will be a general solution. So that's the problem. So it's a nice problem. I actually like this problem a lot because not only, so it brings all of these theories together, okay? It's a differential equation with the non-constant coefficients. So it really brings, so it has to be solved by the Cauchy-Euler form, or this technique of, some kind of a substitution like this, which makes the differential equation with non-constant coefficients into a differential equation with constant coefficients, the type we have already learned to solve. Once we solve that, we put that back in. The factor, the variable t, we put that back in, and we get the sum. We get the solution. But of course, while solving it, we get this new kind of a input which we've not seen before, and really this is the power series solution. It's a new kind of a solution. It's called the power series solution, where instead of a known function, you have a different kind of a function, which if you expand out by Taylor series, you can actually find for the particular solution a power series solution. It's a power series of sine here, okay, and it's a valid solution in that sense, okay. All right, so that's the problem. As I said, it brings all these theories together and ties them into a nice little problem here. And I hope not only this introduces this new topic of power series, but it actually brings in all our previous knowledges together. So anyway, I hope there's something new to be learned from this problem, and will introduce some new content in the next lecture. Thank you.